Hi, this is Pat Frank, and you're listening to the Matt Balaker podcast.
Ladies and gentlemen, thank you once again for tuning in to the Matt Balaker podcast. If you want to earn extra credit, please click subscribe and encourage your friends and casual acquaintances to do the same thing. You guys, I am pumped for today's guest because he is a member of the scientific staff at the Stanford Synchrotron Radiation Light Source. He received his PhD from Stanford University. He has amazing hair and he knows way more about science than I ever will. Please join me in welcoming Pat Frank to the program. How you doing, Pat?
I'm doing fine, Matt, and thank you for having me on. It's a real honor.
Well, it should be, Professor or Dr. Frank, because I took physics for poets in college, and I think I got a B+ in it. So I'd like to think we're, pretty simpatico when it comes to scientific acumen. But now I do podcasting and stand-up comedy, whereas you have continued your pursuits. But I'm curious, Pat, when did you get into science? Like, when did you know you kind of had this scientific bug inside you?
Well, first, let me say that anybody who can get a B+ in physics is definitely top rank in my view.
Oh, thank you. I'm flattered. Yes.
So actually, I guess the first time I realized I liked science was after reading a lot of science fiction as a teenager, was taking chemistry in high school. I really enjoyed it.
And what was it about high school chem that you enjoyed?
It's a really good question. I really can't say. It was just fun. The teacher was named Father. It was a Catholic high school, Father Stronk. Oh. So he signed his name SR for strontium, the element strontium. So he had the sense of humor. So maybe it was that. I don't know.
Was he a Jesuit?
No, he was a Salesian, which is. It's an order that's dedicated to missionary practices.
So missionary practices and combining acids and bases and seeing what happens.
Yeah, I suppose so.
Pat, where did you go to high school?
It was actually Sarah High in San Mateo, California.
So is that where you were raised in San Mateo?
Yeah, no, I was raised in South San Francisco and San Francisco, and we were an immigrant family. My parents, it's a really crazy story. My parents were stuck in Japan during World War II, and
wow.
They spent the whole war there, all the war years, almost starved to death. Had 2 kids during that time, and then me after the war. And
you were the post-war celebration. Congratulations.
In a way, I suppose that's
so. How did they end up in Japan during World War II, Pat?
That's quite a story too. My father was actually born there. His father taught chemistry there, so it kind of runs in the family. So he taught chemistry in Japan. He was married. He was a German chemist married to an English woman. They got a job in Japan. He moved there and had 2 children. So my father grew up there. He spoke Japanese like a native, of course. And my mother was German. She's half Jewish. And she and her mother fled Germany in 1938, a month before Kristallnacht.
Oh, wow.
And took the train across Russia to China and took boat to Japan and lived in Japan for some years before the war. And my mother met my father in 1941, and they married. And my brother Nick was born about 9 months and a day after they married. So
9 months and a day. So
yeah.
We know how they celebrate. Well, it's. I mean, we don't need to make this a World War II discussion, but my mother's family, they were from the former Yugoslavia, but after an invasion, they were forced to Germany, and they were lucky to escape to Chicago.
Wow.
Around the same time, and because of that confluence of events, Pat, we are all here together. So this is pretty exciting time. So you're in school in San Mateo. You liked chemistry. But I mean, I liked chemistry too. And then I became an economics major. What motivated you to continue pursuing science, Pat?
I remember having a conversation with somebody about that, and I told him, he asked me something similar, and I told him that I realized after taking some of it that doing chemistry was the hardest thing I could do well.
Oh.
So that's what I did. And I never regretted it. I enjoyed it, but it was hard, and I did take an economics class, actually, and enjoyed that too. But
I don't think it's as hard as chemistry. That's just my own biased opinion, though.
It gets very mathematical, economics does. And but it was clear that the theory wasn't as clear in economics as it is in science. That the results aren't as hard.
I think fast. Clear as mud is the best way to describe most economic theories, Pat. That's my take.
Yeah.
So you essentially found, to use an econ term, your comparative advantage. You were able to be good at something hard. At
something hard, yeah. And this was at San Francisco State University, a state college at the time, actually, where I did my undergraduate work and got a master's degree. And the department was really small, about 6 professors. They were all really good. They were all very well educated at good universities. And you had one-to-one relationships with all of them. I knew them all. And
so you knew all half dozen of them. That's you're a popular student.
Well, you could talk to them and visit with them. They were friendly, and so it was a great experience there, and it was a very strong major.
And obviously, there are many disciplines within chemistry. What is your focus?
Inorganic biochemistry, which is the biochemistry of trace metals like iron and copper and so on. I got into that at Stanford when I went there. And this is, if you think about the iron in your blood, for example,
okay,
that does the job of carrying oxygen around to all the cells in your body. So how does it do that? Where is it exactly, and how does it interact with oxygen, and what's the chemistry of that? And all of that business is bioinorganic chemistry, the inorganic chemistry, the biological chemistry of inorganic metals. And so there are lots of them. Copper is a big one. There are lots of enzymes in your body that contain copper and do really, really important things that you die if they didn't do. One of the ones that I studied, which was really fun, was vanadium, and that is one that's in the blood of sea squirts, which is our little marine animal. You can find
you're the first guest I've had that was talking about vanadium and fun in the same sentence. So congratulations. and sea squirts. Let's unpack that. What are sea squirts?
Sea squirts are a marine organism that live on wharf pilings. They make their living filtering seawater, but their juvenile form is a little itty-bitty polywog, about 1 millimeter long, that swims around for a few hours after it's hatched out of eggs. They're hermaphrodites, so they just send eggs and sperm out into the water and hope for connection.
They just shoot it out and hope for the best.
Shoot it out, yep.
That was me pre-marriage. Not exactly, but...
Yeah, maybe you don't want to admit that to too many people. But... So these little polywogs swim around, and they have little fins and little eyes and little notochord. And after about 8 hours, they turn over on their head and they resorb all of that and turn into something that looks like an invertebrate, which means they don't have a backbone and they're squishy. So they've been pretty much the same for about 550 million years. Fossil sea squirts have been found, for example, in China that date back to the Cambrian, and they look just like the modern ones.
So if you see a sea squirt now, it's not going to be that different from something a century or two ago. That's good to know.
Well, no more than a century or two. It's more like about 500 million years ago. And they are this polywog form is the primordial form of all the vertebrates. They are our ancient ancestors that turned into fishes, that turned into mammals, that turned into us.
Nice.
So when you see a sea squirt, it's your cousin.
Well, hello, cousin sea squirts. So, but Pat, it wasn't sea squirts that kind of got you on the map, so to speak? Like what you attend Stanford, you have an interest in inorganic chemistry, you discuss Csquirts, and then what are some of the other areas you started diving into scientifically?
One of the first ones actually was back in the 1990s. I got involved in the Creationism Wars.
Oh, wow.
You know, people who wanted to teach creationism in school instead of biology and so on. I got involved in that, and I spent a lot of time arguing creation and science on the very ancient web back then. So I got deeply involved in that and learned a lot. I had to learn a lot of geology and a lot of biology and so on to argue with people who were very sophisticated in the way that they argued, religious extremists who were highly educated, who would misrepresent the truth in very clever ways.
So what, we don't need to dive too deep in this, but in lay terms, what side were you on? Like what did you argue in the?
I argued for science. You have to, if you want to teach biology, you have to teach biology. And the whole business of creationism tried to distort biology and geology and sort of fit it somehow into a religious point of view. And you can do that, but you have to honor the biology and the geology if you want to do that. And they did not do that. And
what do you think were the greatest misconceptions or misgivings on the other side? Like, what did they get wrong? What did they get the most wrong?
One of the things they really seriously got wrong is the interpretation of the fossil record, which is an old story saying that the fossils really didn't say anything about the evolution of animals in the past. And one of the ones that they really got wrong too is the idea that there's evidence that the universe was designed by somebody. It's called intelligent design theory. That was the first, I published a paper on it in a journal of religion and science. It's the first paper I ever wrote that was outside of the strict kind of science that I was doing. And so that the idea that there is evidence that the universe is designed is a very powerful idea, and it's widely held even amongst scientific people. But there's no evidence of that because we don't know how to design a universe. And so if you don't know how to design a universe, you can't say that the universe was designed because you don't know the design concept.
It's very circular, yeah. And you were taught, in a Catholic school. Are you religious or were you religious?
I was as a child. I actually thought about being a priest as a boy. I was raised a Catholic, and I really thought about that hard. And I was ready to go off to seminary.
Oh wow! So you were really in it. It wasn't
I really
just a
was.
cursory
I believed it. Yeah, I really did believe it. But my mother said, you're too young to make that decision, and you should wait till you're after high school. So I did. And by the time I was 18, I had left it all behind me.
You had left religion behind you, or left the priesthood? Okay.
Priesthood and religion, yeah.
And was that kind of a result of this opinion, and not the opinion, but the work you've done in science? Did that influence?
No. One of the things that occurred to me at the time was that if people really believed the religion that they've taught, they would behave differently than they did. So it was like if you spend 7 years with Irish nuns and another 4 years with priests, you realize that they're just people.
Yeah.
And although they talk about their beliefs, they don't live it. And it occurred to me that the idea that there is a God out there who oversees things and who made everything and wants us to behave in certain ways is an extremely powerful idea. And if people really believed it, they would modify their lives extremely in light of that. And they don't.
Okay.
So when I was a teenager, that argument was very central for me. And it was one of the things that led me out, is that people didn't behave the way that they should. Humans have all sorts of problems and inconsistencies and hypocrisies, and that's a whole discussion for a whole other time. But I have a friend, Tim Lee. Hopefully you're listening, Dr. Lee, and he has I think it's a pretty good layperson definition of science. But I don't want to color your opinion. How would you describe what science is to a non-scientist, Pat? It's a methodology. It's a way of thinking about things. And Karl Popper, a philosopher of science, got it right because he observed how Einstein worked. And Einstein famously said that if the redshift, if the orbit of Mercury didn't follow his relativity theory, then the theory is wrong. So science is theory and result, the mixture of those two. It's you come up with an idea about the way things work, and then you do the observation or experiment in order to test your idea. And that's it.
So it's not a static monolith. It's
No.
certainly not a religion, right?
No, it's the way everybody observes goes through the world. Everybody makes approximations for what the world is like, and then lives according to them until they make a really big mistake, and then they have to change their view. And that's science, except it's done quantitatively.
Yeah, and growing up, I remember hearing stories about how at one time it was taught that the Earth was the center of the universe, and
Right.
and through this methodology you discussed, Pat, it was largely refuted, and then it's eventually proven that that it's not. At least in our universe, the sun is the center. I think that's a pretty common understanding. What are some other examples of scientific conventions that are no longer? Like something that was largely believed and then since refuted? And
Well, one of the ones that's really central is that disease was a punishment from God.
wait, it's not?
Not that I know of. So that was a big one. And that was essentially refuted by the French, this famous French, now all of a sudden his name escapes me, but the guy who invented the germ theory in the late 19th century. Pasteur.
I was thinking Louis Pasteur, I thought of it after you said it. So
yeah,
that goes to you.
So that's one of them. Another one is that, the origin of the Earth and Noah's flood. That was a big one. And in 1835, there was a meeting of the Primordial Geological Society that said, we've been spending 50 years looking for evidence of the flood, and we can't find it. So they have to abandon it. It was abandoned as a geological theory in 1835.
Wow.
And at about the same time, there was a French astronomer who was able to calculate the distance to the nearest stars and found out that they were an enormous distance away. And the universe then expanded from just being our solar system with a bunch of stars, that were nearby as little points of light, to being this enormous place where we were just a small part of a gigantic space. I used to know his name. I still do. It's not coming back because I haven't, thought about it for this.
I won't quiz you on it,
yeah. But so these are ideas, that were very prevalent. The universe is a really small place. Even though the sun's at our center, it was like the universe ended at our solar system.
Mm-hmm.
But he found out that it didn't. And then the whole flood geology went away, which was one of the big creationists' bugbears, is flood geology. And then there's the germ theory and the idea that storms, lightning, for example, is the punishment of God. That went away with the lightning rod and the understanding of lightning. So lots and lots of ideas that were used to organize the world went away. Another one, actually, that went away during the Enlightenment was the belief in witchcraft, which I've been reading about.
I think we might have to revisit that. That's just my opinion. I think there might be evidence of witches around me, but that's just, again, my own anecdotal experience.
Yeah.
So obviously I'm joking about that, but it brings up an important point. Like there are conventions and beliefs that a lot of us have, and over time they can be shot down or they can be refuted, and new evidence can emerge, and hopefully sane-minded people can, discuss this evidence and revise their beliefs.
Sure.
You've delved into areas beyond just, was a sea squirts. You wrote a paper that you were kind enough to send me on climate change, or I think more broadly, discussing climate models. I read it, and thank you for writing it in a way that lay people can understand. I think that's super important. But for our audience, do you mind just kind of summarizing some of the key takeaways in the paper?
Sure. Well, the first thing that people might say who are critical of me saying anything about climate is that I'm not a climate scientist. So that would negate anything I would say further to lots of people. But the paper that you read, it was an op-ed, but the paper that it's based upon isn't about the climate per se. It's about physical error analysis. How do you know your data is any good?
Yeah.
And that's something that every scientist works on. How do you find out whether your data is any good?
How do you find out whether your data is any good?
Yeah, well, that's the thing. One of the things when you learn chemistry, one of the things you have to take is analytical chemistry, where you worry exactly about that. And one of the things that you have is a standard against which to measure your instrument. You know what the true value is with a standard, and you use your instrument to investigate the standard, and if it gives you the right answer, then the instrument is good. If it gives you the wrong answer, then your instrument is bad, and all the data you've collected off of it, is worthless.
But it's contingent on knowing the right answer.
Correct.
So obviously in situations where we don't know the right answer, we're kind of like shooting at something. And then I think you use this example of moving a target where the bullet holes are.
That's called the Texas sharpshooter fallacy.
And can you share with our audience the Texas sharpshooter fallacy?
Sure. Texas sharpshooter goes up to a barn and pulls out his gun and shoots a bunch of holes in the barn wall, and then draws the target where the bullets are clustered.
And I think this would apply to other states beyond Texas, but I think it's an important message. And central to your paper was a distinction between accuracy and precision.
Yeah, well, let me talk a little bit about how I got involved in this.
Oh, sure.
Business, right?
Yeah, because as a non-climate scientist,
there I was. I would have been very happy to just be an obscure scientist working, on Squirts.
It wouldn't be. Please continue.
Well, but you don't know Squirts the way I do.
No, I definitely don't.
So I got involved back in 2001 when the third assessment report came out from the international, the climate change group, the UN climate change group, the IPCC. And the Intergovernmental Panel on Climate Change, so the official body. So this 2001 report came out, and there was a lot of really critical polemics about it in newspapers and so on and so forth. And I really got tired of reading polemics, and I wanted to know for myself whether or not there was a problem there, because you want to know.
Sure.
So I started reading the primary climate literature, and when you go in something like that cold, it's really complicated. I was just sort of.
I think going in warm for me would be complicated, but please continue.
It's complicated business. And I investigated that for about 2 years and was not making much progress because you don't know how to think about it. Until I ran into a paper by a group, Willie Soon and Sally Baliunas and their colleagues, Craig Idso, 5 people on this paper. And it talked about climate models and the mistakes climate models make. And all of the people who wrote it were physicists, this paper. In fact, Sally Baliunas would be a terrific person for you to interview on your podcast.
Hit me up, Sally.
So they wrote this paper about climate models, and they make these climate models make enormous errors when they simulate the climate. In the ocean, they make errors in how the ocean works and how the atmosphere works, and so on. And I read this paper and I realized that the UN government body, the IPCC, couldn't possibly know what they're talking about. They couldn't possibly know the things that they claim to know.
Wait, are you questioning the UN, Pat?
I am, actually, yeah.
Please continue.
So I realized they couldn't possibly know. And that, the scales fell from my eyes. That was my Damascus moment.
Okay.
Yeah. And I suddenly realized that what I have to look at is the basis of the claims, not the claims themselves, but what are they based on? And then I read the papers again with these new light, and I noticed that all of the arguments that they made, the charts that they drew, the lines and so on, never had any error bars. And if you don't have error bars on your numbers, we don't know how reliable they are. There are 10 people outside. Well, how do you know? You look outside and there are only 3. And so,
but plus or minus 2 billion, I guess.
Yeah, there we go. So the plus or minus is really critically important. And that's what really got me started. And so by 2008, I was confident enough, after sweating bullets over this, to write a paper that was published in Skeptic magazine after peer review, if you can believe that.
So it was first peer-reviewed and then published in Skeptic magazine. And then what was the kind of summary of what was published in Skeptic, Pat?
It was pretty much the same as that paper that you read, which is that climate models can't predict the climate. And if you look at the mistakes that the climate models make, the uncertainties are so gigantic that essentially you know nothing. And so it's possible to adjust the model so that it looks like it's making all kinds of really good predictions. Mm-hmm. And these days with computers, you can make terrific pictures of the Earth with clouds and this and that and something else, and it looks just like, a telescopic image of the Earth from above, but it's all wrong. It looks real, but it isn't.
And how do we know it's wrong, Pat?
Because the errors and uncertainties of those pictures are hidden because you don't know what the reality is, right? So you can make a picture of the Earth using a computer with false colored diagrams where the oceans are blue and the land is brown and the clouds are up there and it looks just like, but it's the details that you have to get right in order to understand what the climate is really doing. One example, I'll give you an example. The oceans. You look at the oceans and the theory about the oceans and how they work. You have something called the thermohaline current, which
thermohaline current. Interesting.
Yeah, which carries salty water from the equators up to the north and deposits the heat, in the cold north and circulates back down again. And that's been the theory about how the ocean works since at least the 1950s and even earlier. And there are pictures that you can see of these currents with the streams going up and all around and so on and so forth. Well, it turns out that someone put some what are called neutral buoyancy buoys in the ocean to try and track the currents. So they would drop these buoys, and there are several hundred of them, and they'd go down thousands of feet looking for this current, and every day they would surface, tell you where they are, go back down, and then, and you could track them. And so what they found is no evidence for any current like that. You look at the trajectories of these buoys, and they're circulating this way, and then they're going that way, and then they're going up here, and then they're going down there, and they're not drifting to the north the way they should have gone. So this whole idea of the thermohaline current, there's a really famous marine physicist, Carl Wunsch, who says it's a really great cocktail party conversation to have. But, and then you have these computer models that incorporate the wrong model of the ocean. And the models themselves have to do something called converge. When you run a model, it's supposed to converge on a single result, 10, whatever. And if they don't converge, you don't know. Because, it might be 10, it might be 20, it might be 50, it might be 0. Who knows? If the model doesn't converge, you don't know what the answer is. And so the ocean models don't converge. They don't give you a single answer about the state that the ocean is in when you're trying to model it.
Well, and the little I know about science, Pat, is not having answers is a lot more common than having an answer, right? Like you can have a proper methodology and I think it's so easier. It's so much more like neat when we can say, all right, the answer is X. Mm-hmm. But the reality is we don't know a lot of things. And I think not knowing makes people think that it's poor science. What say you?
I think saying I don't know is one of the strongest things that a scientist can say. And
I will say, I think it's one of the strongest things a person can say.
And say, period. Yeah. It's really hard to someone who can cheerfully admit ignorance is somebody that you can trust. And it's a real test. So there are things we don't know. We don't know most things, but we do know a lot more than we used to. And one of the things we know is how hard it is to know anything. And it really is hard to know something. There are these videos out, Feynman's videos. You've probably heard his name. He was a very famous physicist, and he made videos. You can find them on YouTube, Richard Feynman. And he talks. There's an interview of him where he's being asked about knowledge, and he says I know how hard it is to know something. He's a brilliant physicist, and he said, I've looked at some of the social science stuff. He says, and they claim to know things. He says, but when you look at it, there really isn't knowledge there. There's just assertion. And to be able to tell the difference between someone claiming to know something and someone who actually knows something, if you're not a practitioner in the field, it's really hard to tell the difference. But it's extremely difficult to know something. And as someone who tried to figure out what was going on inside the blood cells of sea squirts, for example, it was really, really, really hard. And there was a lot of stuff out there where that was wrong. So it's hard to know anything. And which is one of the reasons why uncertainty bars and error bars are important to have, because it tells you how reliable the knowledge is that you claim to have.
Yeah, I mean, I think just questioning the accuracy of something, is so important. I mean, when I took high school physics, I'll use this as a crude example, and please shoot it down. You're in Northern California, I'm in Southern California. I think it would be accurate to say it takes about an hour to fly from LA to San Francisco. It would be precise but inaccurate to say it takes 865,000 days, 23 hours, and 0.26 milliseconds. So the point is, like, accuracy is precision is a measure of the instrumentation, like how fine the significant figures can be, so to speak. But you can be precise but completely wrong. Like it doesn't take days to get to San Francisco from LA with an airplane. How does this apply to a kind of the zeal with climate change and climate science?
Yeah. So precision really is how often you can get the same number from your instrument. Okay. If you have a ruler and you're going to measure a room because you're going to paint it or do some furniture repair or whatever, you measure with your ruler, and if you get the same number every time, your ruler is precise. But if all of your inches are actually 3/4 of an inch, then your number is wrong, and you're going to make big mistakes, right? So the accuracy is the correct number, and the precision is how often you get the same number.
Gotcha. Okay.
So those are different. Those are different. So you can have a really precise measurement, but it's wrong because you get the same number every time with your ruler, but your inches are wrong. Right?
We all want to have the right inches.
That's what I got involved in with this climate business. And
go ahead.
The problem with the whole trying to publish a paper in that field is that it's heavily politicized.
What?
And people have a narrative about what they want you to believe and what they want to believe, right? And the narrative is that all of this horrible stuff is happening and we're all going to die in a hot future, and carbon dioxide is making the climate warm up, and it's all our fault, and we're a virus on the planet.
Shame, shame, shame,
shame. Yeah, shame.
So, do we know it could just be punishment from God?
It could be. Yeah, it could be. Yeah.
So you say, and please go ahead. Sorry.
Yeah. So the question is that all true? And when you try and publish a critical thing in an area where everybody is committed to one point of view, and where there are consequences that are laid against people who divert from that point of view, it becomes really difficult. There's this old saying that truth-telling in a time of deceit is a radical act.
Right. So I think, God, that's so important. What you just said, and so I don't want to just skip past it, but why is there such a singular consensus, in your opinion, Pat, when it comes to climate change or climate science right now?
Why is the consensus so singular?
Yeah, like why is it like you're voicing some dissent, and if you were talking about sea squirts, people wouldn't care, or they may be like they'd review it critically, but you're not getting that. What do you theorize?
I have a pretty good idea about that. One of them, which is going to surprise you, goes back to 1996 and the Telecommunications Act that Bill Clinton signed, and it allowed media companies to buy up all the media in a given market.
Huh.
It used to be that you could if you owned newspapers, you couldn't own the TV stations, and if you owned the radios, you couldn't own the newspapers. So there were a diversity of voices in every market. But now that diversity is all gone. He signed this legislation. Media companies bought up all the media in the markets, and now you have just one voice. And all the media is now owned by just a couple of companies. And so all the people who are in the media tell the same story, whatever it is.
And what story is that?
That climate change is happening and that it's all our fault. So whatever the current idea fixe is amongst the media giants, that's what they report. And they decide what to report and what not to report, how to slant a particular story, whether they talk about a story at all, that sort of thing.
Yeah, it used to be the saying was good news doesn't sell newspapers. Now I think it's good news doesn't lead to clicks. But it's the same idea.
Yeah. Well, huge amounts of money have gone into this climate change things, like literally trillions. All those windmills that you see up on the mountaintops there in California, they're all subsidized. So huge amounts of money go to the people who build those windmills in the subsidies coming from the government, coming from middle-class pockets as tax.
Oh, sure. And I mean, I'm trying to do some work in our home, and we have to put solar panels up.
There you go.
We're forced to, and I'm not saying, I don't know enough about the merits of it for a particular location, but when you have this sort of agreement where it's like, if you do this, you have no choice but to put solar panels. I mean, that kind of extends to what you're saying. It's like, if you want to be a tenured professor, you have to more or less abide by consensus. I mean, it seems that way.
That's true. Yeah, there is a lot of that, and professors have been fired for saying the wrong thing. And I don't mean going after an undergraduate or whatever, but Peter Ridd in Australia, for example, was fired from the university for saying that the Great Barrier Reef was in fine shape based on his research and his knowledge.
Well, it also like. One, that's crazy. Not because I can, verify what he said is true or not, but just like the whole basis of this methodology we call science is predicated on people disagreeing or at least questioning models, right, and having the freedom to voice those. Like, right, what happens if we're only hearing from one side?
Yeah, then disaster happens. Richard Feynman says that science is belief in the ignorance of experts. and that really is it. That captures in a nutshell exactly what you just said.
So you say, I want to dive into this a little bit, but in your paper that there's no reason for young adults to despair about their lives. There's no reason to avoid the joys of raising a family or the happiness of sending your children off into the future. That kind of flies in the face of a lot of conventions. Like, why should I believe what you wrote?
Well, if you read my paper, you'd see that climate models have no predictive value. There's all of these projections of the future that, the thermal future that they have, and all those raising lines going up into thermal disaster, none of them are correct. It's an absolute fact that it's not a question of yes or no. It's a question of do you know? So the thing is that carbon dioxide might be warming the climate, but nobody knows. So in the absence of theory, which won't tell you the answer about whether CO2 has an impact on the climate or not, you look at history. And our history is very good, and it goes back in geology. It goes back billions of years. So we have ideas about what the climate was like billions of years ago, right up into the present. And carbon dioxide, here's something that you probably didn't know. All of the carbonates that you have, the White Cliffs of Dover and all of that, all the calcium carbonate stone that's in the ground, all of that carbon.
And lots of my shower too.
There you go. Yeah.
We don't have a water softener, but please continue.
We can talk. Well, anyway, so all of the CO2 that's bound up in carbonates used to be in the atmosphere. All of it. And if you calculate how much that is, there were about 60 to 100 atmospheres worth of carbon dioxide in our atmosphere. So it's not 0.04%, which is what we have now, but it was like about 99.999% CO2, and it would be a crushing weight of 100 times the weight of the atmosphere that's on you now, which means 1,400 pounds per square inch instead of 14 of carbon dioxide, and it all went away. Where did it go? Right? It all went into the oceans as carbonate and precipitated out. So, and that took a long time. And so there have been huge amounts of CO2 in the atmosphere before, and nothing ever happened as far as, thermal runaway is concerned. So even a few million years ago, there were several thousand parts per million, 10 times more than there is now. Nothing happened. Temperature went up, temperature went down, You look at the geological history and compare the air temperature of what we know of it and the carbon dioxide, and there's no correlation at all. And even in the last ice ages, where one of the really popular pictures that are published are the ice age temperatures going up and down like a sawtooth, and CO2 goes up and down like a sawtooth at the same time, except that it's always the temperature that goes up first and then CO2 follows. And then the temperature turns over and goes down, and then CO2 follows, because CO2 dissolves into the ocean when it's cold, and it comes out of the ocean when it warms up. And so the warming and the cooling happen first, and the CO2 go up and down afterwards. So there's no evidence in there that CO2 is driving the temperature at all. And if you look back over billions of years of Earth history, CO2 never has any correlation with the temperature that's going on.
What does have correlation with temperature changes?
Some people say it's the way the sun behaves. And, the sun really does drive our climate. It's the whole source of all the energy that comes into Earth. But there's a lot of controversy about whether or not it drives the details, day to day, year to year, decade to decade, whether the changes in the sun correlate with that. And that's a big fight amongst astrophysicists and those kinds of people, atmospheric physicists.
Interesting. Well, now that I have your ear, it seems like every couple of years or more frequent, there's a Hurricane Katrina. There's events like we had in Iowa with flooding. Yeah. There's fires as a result of drought. Yeah. Inevitably, and I get all my scientific data from my Facebook feed from my friends who avoided any class with a calculator, and they're now experts. No, I kid, but inevitably, Pat, it seems like some awful natural disaster will happen, and people will point to climate change. And again, I'm not saying it's the result of it or isn't. What I'm saying is I don't know. Like I don't have the knowledge to.
Well, I did.
How would you counter? Like if someone says like, all right, this flood, pick the latest one. That happened. Like.
Well, so the question is
what say you?
Are floods like that unusual over the historical record? Have there ever been floods before? And if so, how big were they? And that's what you have to know.
Well,
right?
200 years ago, they weren't on Google News. I guess
that's the problem, is that people just get focused in on the local news and don't broaden their perspective out to take up the historical news. And I'll give you an example that I discovered just by accident once. And that is, I was reading a paper of geology. This was back in my creationism days. And I found a paper that discussed a hydrologic event on the Sacramento River that was discovered by people who were, putting a core down into the base of the river to get a geological sample there. And they found out that 600 years ago, there was a hydrological event on the Sacramento River that removed hundreds of feet of sediment. A hydrological event means a gigantic amount of water came flowing down the Sacramento River for reasons that still were obscure. But it was a huge event, and it removed a large amount of dirt from the bottom of the river, like hundreds of feet. Mm-hmm. So if that happened now, San Francisco would be gone.
Right.
And so that happened 600 years ago when there was no CO2 going on at all. And so there was CO2 in the atmosphere, but there wasn't any big climate change associated with it. It happened when CO2 was down around 200 parts per million. So now 600 years, about 280 parts per million back then. Yeah. So, here was this giant event. It was a huge natural disaster, and it had no connection at all. So there have been natural disasters like that all along, floods and droughts and hailstorms. There used to be a Smithsonian Institute called the Smithsonian Institute for Short-Lived Phenomena, and they would record all of these things. I've got one of their really early journals, and they stopped doing that, unfortunately. But you read through there, and they talk about all of these short-lived phenomena that happen. A sudden hailstorm comes up, and giant hail falls and destroys an entire village. And, you can find things like that in there.
Wow.
And so things like that always go on. There are always going to be extremes. And so any extreme that happens, they say it's because of the warming climate. Maybe it is, but the question is whether the warming climate is our fault or not.
Okay. Well, I guess I have a question. If the climate is warming, call it 1 degree Celsius in pre-industrial times, regardless of the cause, is that dangerous for us? And should we modify our lifestyles?
No.
Why?
No. Well, if the temperature goes up, the 1 degree, if you think about the Earth and you have the latitudes, you have the tropics where it's hot all the time and then it cools off towards the poles. So if those climate change does happen, that means that the average climate is going to go north by about 100 miles or so. So that means, that the climate that's now in LA ends up in Stockton.
Okay.
Or someplace north, 100 miles north of LA. That's climate change. So everything will be just a little bit warmer, and so what? Is that bad? Why is that bad?
Well, if nothing is correspondingly cooler, I'm not knowledgeable enough, but my thing would be like nature's delicate. And these small changes can have major ramifications.
No, nature isn't delicate. Nature is really robust. And here's an example, from history. When the Hannibal and the Carthaginians came and sent their elephants over the Alps to attack the Romans, how did they do that if there are glaciers everywhere? There was a Roman warm period. There was a warm period during those times when it was warmer than it is now by probably 1 degree, and the glaciers had melted back, and there were passes over the Alps that are now glaciated. And, Hannibal sent his elephants over there and attacked the Romans. In fact, even now that things are warming up again, as the glaciers retreat in the Alps, artifacts are being found of things that people left behind that got covered over with ice later. Stone tools or leather items or carved objects, bits that that were covered over. So it was warmer back then. There are even evidences of forests that were growing where they're now too cold to grow back then. One of the big indications is something called the northern tree line. You go up into Siberia or northern Canada, you go far enough north and the trees don't grow anymore because it's too cold, right? But during the medieval times, there was a medieval warm period that lasted for about 500 years, where the forests advanced north, the forest line advanced to the north. And then it got cold again during the Little Ice Age, and all those forests died, and they left stumps behind. So there are what are called pre-fossil stumps of forests which used to be in the north and aren't there anymore because it's gotten too cold. It got too cold during the Little Ice Age. And the forests are now advancing north again, slowly, but they still haven't reached where they were, the position that in the north that they were during the medieval warm period.
Wow. Well, sorry, I have a precocious 10-year-old who loves science. He watches a lot of Mark Rober videos. And I know there's going to be a situation where he comes home from school and says, teacher so-and-so says climate change is a result of man-made interactions or
it's our fault. Yeah.
It's more or less. How would I describe this to a 10-year-old? What would you say I should tell him if that's his belief?
How does the teacher know? That's what I would ask him. Does the teacher
because because lots of people said, and generally the scientific consensus, if you go on ChatGPT, for instance, and say, is climate change man-made, which I did before this, there's lots of, I'm using evidence in quotes, but I mean, that is kind of a result of a lot of people putting opinions in.
Yeah.
Go ahead. Sorry.
Yeah, I mean, there's, for every bit of artificial intelligence, there's got to be artificial stupidity, right? AS instead of AI, and so the artificial intelligence only knows what people feed into it, and so of course you're going to get conventional answers out of it. But
generally, convention happens because generally, I'd argue that there's enough evidence supporting that. Why
is that true of witchcraft? Is that true of the flat Earth? The ancient.
Yeah, but they've since been refuted. I guess we're saying climate, the alarmism of climate change. Is that the new witchcraft? I guess that is it just too early to have enough voices like yours, where people kind of poke holes in the convention and a new consensus forms?
Yeah, there are lots of voices out there like mine, except that you never hear about them because they just kept off of the media, or they're disparaged.
And what, I have a theory, at least when it comes to politicians, and I don't want to make this a political show, but I would tend to buy into what politicians say about climate change more if the result wasn't 9 out of 10 times, that's why you need to give more power to us so we can do X, Y, and Z. It's like, it seems to me, and I'm no scientist, as a means to garner more influence and power. Therefore, I'm skeptical of it. Why do you think politicians, and I think this crosses party lines, are so one-sided when it comes to climate science?
Well, I don't think that they are. Conservative ones aren't, for sure. But
I guess they're not on the news or something.
The real problem with this business, first, is that nobody has ever put together a commission of impartial people to actually examine, for example, the climate models that are used to build airplanes, for example. They're very complicated models. They involve a lot of calculus and who knows what all. And they have to go through what's called a validation and verification process, where impartial third parties who are really, really knowledgeable and understand numerical methods and so on, computer calculations, have to go through the model and find out whether the equations actually solve the problem and whether the whole program operates the way that the people who wrote it say that it does. Third parties have to do that. Climate models have never, ever been subjected to a verification and validation process, ever. And you ask climate models about that, and they get very angry, and they don't want to do it. So it's never been done. And politicians who are interested in resolving the question would have required that. They should have required a validation of climate models by impartial third parties who are out there. But
why, when we can just watch Inconvenient Truth? Well, isn't that easier?
Right. And so there's that. And the other thing is the air temperature business. This rising air temperature that we all see these plots of. That's going up like that, or maybe if they're going up like that, depending upon your point of view. The people who do those, who make those, pay no attention to the instruments. How good are they? Do they make mistakes? And it's all just brushed under the carpet. So the problem is that the verification and validations have not been done, and the scientific societies, for example, the American Physical Society and the American Chemical Society, and all these scientific bodies that are supposed to protect and defend science, stay silent, or else they buy into it for reasons that are very obscure. They haven't done the due diligence themselves, these scientific societies. Neither has the Academy of Sciences. They just go along with it. And so the question is why? And, that's been the conundrum that I've been struggling with all along.
Yeah. And why have you been able to, where does this courage come from for you? Because you're very kind of gentle. You're easy to talk to. You're not a big, flamethrower. Like,
no, I'm not, and I'm not a big guy either, but I'm compelled to do it. When I found out for myself, when I looked into it myself, and found out that they couldn't possibly know what they're talking about, and science and reason are the sources of everything that's worthwhile in our society. All of our virtues come from science and reason, because if you don't have those two things to nail down some ideas of being either right or wrong, you have no benchmarks, no mileposts for when you're going insane.
That's true.
You think about the Enlightenment, right? When did they stop burning witches? Well, it was during the Enlightenment in the late 18th century, when science and reason finally came to the fore, and everybody said, this is nonsense. We have to stop it.
Mm-hmm.
And all of our humanism came from science and reason. And, the whole business of racism got thrown out of the window when we discovered from genetics, for example, that everybody is the same. There's just no point to it. And so all of that comes from science. All of the good things that we have, all of our virtues come out of science and reason. And here we have people who were abusing science to some obscure end and distorting what's going on and not doing it the way it should be done and making claims that they can't defend, at least not to someone who knows what they're talking about. And they're essentially bringing disrepute on science and making it a method of constructing a convincing seeming lie. And
wow.
I'm sorry to say that that's what's going on.
Well, I'm glad you shared it. And how is the reaction among the scientific community? Like, when you're willing to take, how have people reacted to you, Pat?
Well,
and colleagues and people with PhDs and advanced degrees and whatnot.
I've known some very, very sharp people with PhDs in physics, and they run away from it. They don't want to deal with it because it's dangerous. And I've had colleagues that I've known for years who put me in a different category of person as a consequence of my skepticism.
Wow.
So it becomes very difficult. And people
you mean universities aren't these bastions of tolerance that I was taught to believe, Pat?
That's a whole other subject, and the answer is no.
Well, I do want to talk about that maybe on a subsequent episode, but we are kind of coming into the time limit. But I want to know what professionally, Pat, what are you most proud of that you've done? What am I? I've never thought about that, and aside from being on this show, of course, that is an honor, I have to say, and I thank you for that. But I don't think about being proud of anything, but I think I'm happy about certain things. I in the course of my career, which is almost over now, I'm pretty much retired from Stanford, but I have colleagues whose respect I've earned, and they're really smart people. The people I've worked with, I've earned their respect, and I've had people contact me internationally who want to collaborate because they like my work. So that's the sort of thing that I'm really happy about, that that my work is sufficiently good that other people whom I admire honor me for it. And so if it's anything, it's that, earning the respect of my peers by dint of effort. By dint of effort. As an immigrant kid. An immigrant kid who ended up teaching at a place called Stanford University. I didn't teach there. I was scientific staff. I'm not on the faculty. Staff. Point taken. I did some teaching, substituting in for people who weren't there. And I've helped graduate students and postdocs get their degrees and do their work after I finished, going through my gauntlet of courses and so on.
So that's all been good, and I've been able to mentor people. That's been good. I've been able to help people get their degrees. That's been good. I was the chemistry safety person at SLAC for a long time. So I got involved in a lot of safety issues and reconciling problems and helping experimenters doing their work safely, all that sort of thing. It's very satisfying work. And I was happy with that.
I can only imagine. Well, where can people learn more about you and your work?
Well, the video that you talked about early on would be a good one if they're interested in the climate change one. That was a talk I gave for the Doctors for Disaster Preparedness. But, I don't have a blog, and nobody's interested in doing news stories about the fact that climate models have no predictive value and that the air temperature record is pretty much a crock. So they don't want to talk to me about that.
Well, they should.
Yeah, maybe. But let me just say that I recently became a member of the CO2 Coalition. It's a group of about 130 scientists who think pretty much the same way I do, all across all the disciplines, from geology through chemistry through physics. And they actually put out literature on the kinds of things that I've been saying, including children's books. So if you wanted to buy a book for your kid, you can get one from them. And that would be useful for school too. They even have teaching programs.
Well, I'd love to get more diversity of thought in schools across the country. So that'd be a nice change.
The head of the CO2 Coalition, his name is Gregory Whitestone, and he's a really good guy. And he's actually written a book called The Inconvenient Facts, which is the #1 on Amazon for ecology books. So they're out there. The people are out there. It's just that they get excluded.
Well, I'm not going to exclude you from this program, Pat. Dr. Patrick Frank, thank you so much for joining us today on the Matt Balaker podcast. We really appreciate it.
Thank you, Matt. I was honored to be here.
Thank you for listening to this episode of the Matt Balaker podcast. To learn more, please check out mattbalaker.com and encourage your friends to like, subscribe, and share. Really appreciate it.